Hello everybody and welcome to our video on series. So let's start off with a definition. Given a sequence a sub n, the nth partial sum of a sub n is the sum from I equals 1 to n of a sub I. So we take the n terms from the sequence and we add them all together. And s sub n is what we use to denote the sum of those n terms. All right, now given a sequence, the series of those terms, a sub n, is defined to be the limit of that partial sum, right? So the limit as n goes to infinity of the sum from I equals 1 to n of a sub I. So in other words, this is exactly the same thing as just writing equals the limit as n goes to infinity of s sub n. So when we talk about a series, all we're asking is what happens when we take the limit of the partial sums of terms, right? So now we're not just looking at what are the terms doing, but specifically what's happening when we add the terms together. If this limit as n goes to infinity of s sub n exists, then we say that the series s equal to the infinite sum from n equals 1 to infinity of a sub n is convergent, which is our standard language. If the limit exists, it's convergent. On the other hand, if the limit of the partial sums does not exist, then we say that the series of terms from n equals 1 to infinity of a sub n is divergent. All right, so let's take a look at some examples here. And this is just to kind of introduce you to some things that you've already seen before but may not have thought of in this terminology yet, so we can kind of tie this notation all together. So here we have a sequence. Pi is a sequence of terms being added together. So the sequence looks like a1 is 3, a2 is 1/10, a3 is 4 over 10 squared, so forth and so on. But what I'm concerned with is the number pi, which is the sum of all of these terms in the sequence. So what do we know about these sums? So if I look at the first partial sum, that means just add the first term by itself. And the second partial sum is 3 plus 1/10. And of course that's 3.1. And the second partial sum is 3 plus 1/10, or sorry, the third partial sum is 3 plus 1/10 plus 4 over 10 squared, which is 3.14. And so forth and so on, right? So these are the partial sums for different n values. And what does that tell us? Well, it tells us a couple things. We can see just by the way this expression is set up, every term adds to the number. So s sub n is increasing, but it's also bounded, right? All of these terms are greater than or equal to 3, and they are also all less than 4, right? Because each number we add moves to the next decimal place. We're never going to add up enough to get to 4. We're never going to add up enough to get to even 3.15, of course, but it's sufficient just to find some bound to say, hey, now we know this thing is increasing and bounded, and that implies that the partial sums converge by the monotonic sequence theorem. So S sub n is a sequence of partial sums of terms. So we're starting with the sequence a sub n, we're taking partial sums, and that generates a new sequence s sub n. That's what happens when you add all the terms together. And we can use, say, our monotonic sequence theorem to determine if that partial sum converges. In this case, it does. And that's how we know pi is a finite number. Right? We can figure out descriptions of pi in terms of series, but this shows us that that result is actually a finite number. Okay, so now let's take a look at another kind of standard example here. 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... So we are taking the infinite sum of terms that look like this. And so let's take a look at what these partial sums look like. So we want to show that this is actually equal to 1. So the first partial sum is just 1/2. And the second partial sum is 1/2 plus 1/4, which is 3/4. And the third partial sum is 1/2 plus 1/4 plus 1/8, which is 7/8. And so hopefully what we see here is that as we increase the expression's n value, what we always end up getting is a power of 2 in the denominator and 1 less than that number in the numerator. So in other words, s sub n is always going to look like 2 to the nth power on the denominator and 2 to the nth power minus 1 on the numerator. So if I wanted to evaluate the series, and how do we write this series? We write it as the sum from n equals 1 to infinity of 1 over 2 to the I power, or to the nth power. Yeah, sorry, we're using n here, mixing up my letters. So this infinite sum is the limit of the partial sums. But that means I'm taking the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. So if I split that fraction up on the difference there, 2 to the n over 2 to the n is 1 minus 1 over 2 to the n. And so this term goes to 0. So this whole thing is 1 minus 0, which is 1. So that shows us that the sum of these terms approaches 1. And so we say the series is equal to 1 because the series is the limit of those partial sums. Okay, let's take a look at another example. Here we've got the infinite sum 2 plus 2 plus 2 plus 2, so forth and so on. So my partial sum looks like 2 for S1. S2 is the first two terms added, 2 plus 2, which is 4. S3 is the first three sums added, which is 6. And in general, what are we doing? We are repeatedly adding 2. So we see that the nth partial sum is just 2 times n because repeated addition is multiplication. So then the series of n's from n equals 1 to infinity, where I add 2 over and over, is the same thing as the limit as n goes to infinity of 2n, which is infinity. So this implies that this series diverges. I should have specified maybe in the second problem, I did in the first, but I should have specified in the second one that, yeah, hey, we got a value for that limit, so it converges. So the series converges. Okay, so that's the whole idea here, is that we're looking at adding these terms together, looking at their partial sums, and asking what value do these partial sums approach. But of course, these types of partial sums that we can so easily determine convergence for, or in the case of examples 2 and 3, actually evaluate those limits, that's not always a trivial matter. So we have to develop some more theorems to deal with more general cases. And with that in mind, let's tackle another case. So a definition, a series that can be expressed in the form, the sum from n equals 1 to infinity of a times r to the n minus 1, which looks like a plus ar squared plus ... where a is not 0, is called a geometric series. So now we're going to take a look at what the partial sums for that geometric series look like. So theorem, the nth partial sum of a geometric series is S sub n equal to the sum from I equals 1 to n of a times r to the, that's a typo, that should be I minus 1. Please fix that. Okay, that should have been I minus 1, because what's varying here is I equals 1 to n is our stopping point for our sum in this case, equals a times 1 minus r to the n over 1 minus r. Okay, so how do we prove that this formula is true? And of course, this only applies for r not equal to 1, because if r was equal to 1, we would be dividing by 0 here. All right, but let's take a look. S sub n is a plus ar squared plus dot dot dot, and I stop at the value I get when I plug n into this expression, which is a times r to the n minus 1. Now what I'm going to do here is I'm going to write out r times s sub n. So the same sequence, but I'm going to multiply every term by r, and then that'll give me ar plus ar squared plus dot 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 plus a times r to the n minus 1 plus a times r to the n. So I have the same number of terms, it's just each term is one higher power than the terms in S sub n. And now I'm going to do something very clever, which is subtract the two terms. So S sub n minus r times S sub n, and I subtract here and here, and notice that all the terms I've lined up are going to cancel, so I get left with just a minus a times r to the n. So I factor out my S sub n, I factor out a, and then I have my sum. Divide out the 1 minus r, I get S sub n equals a times 1 minus r to the n over 1 minus r, as long as r is not equal to 1. So this formula allows me to deal with nth partial sums of geometric series. But of course, how do I deal with the actual geometric series itself, the infinitely many terms? And for that, we have the geometric series theorem. So the geometric series theorem says that if the absolute value of r is less than 1, then the series from n equals 1 to infinity of a times r to the n minus 1 is convergent, and therefore, another typo. How did so many typos slip by on this thing? Let me go ahead and fix that one real quick. And the sum of terms from n equals 1 to infinity of a times r to the n minus 1 equals a over 1 minus r. On the other hand, if the absolute value of r is greater than or equal to 1, then the sum is divergent. So how are we going to prove this? Well, we're going to prove it primarily by looking at the nth partial sum formula and taking limits. But first, we'll consider the special case if r equals 1. So if r equals 1, this is really just a, the sum of a from 1 to infinity, which is a plus a plus a plus a. And we've already seen something like that. That partial sum looks like a times n. And so the limit of that partial sum is obviously infinity, and the series diverges. Now recall from our section on sequences that the limit as n goes to infinity of r to the n is 0 if r is between -1 and 1. It's 1 if r equals 1, and it does not exist otherwise. So if I take r equal to -1, and I take the limit as n goes to infinity of the partial sum formula, so I just plugged r equals to -1 in there, this is divergent because this term diverges. Right? And the rest of the terms are constant, so this whole thing diverges. On the other hand, the absolute value of r is greater than 1, then this diverges since we know that the limit of r to the n diverges. in general whenever the absolute value of r is greater than 1. Finally, if the absolute value of r is less than 1, then when I take the limit of partial sums, I know that this r sub n is going to go to 0. And so we get the limit as n goes to infinity of s sub n is a times 1 over 1 minus r. So altogether, that we summarize as saying the series converges to a over 1 minus r when the absolute value of r is less than 1. Now, one little addendum I want to throw on there, just to help you out with some future problems. R, as used in the geometric series, is called the common ratio, and it can always be found by dividing any term by the previous term. So if I get a sub n divided by a sub n minus 1, that's a times r to the n minus 1 over a times r to the n minus 2. And when we simplify that, we get r. So one of the ways you can figure out if something is a geometric series is by dividing a term by the previous term and seeing if you always get the same number. That would tell you it's geometric. Now, with that in mind, let's take a look at example 4 here. Determine whether the series is convergent or divergent. If it is convergent, find its sum. So we've got 20 minus 5 plus 5 fourths minus 5 sixteenths. So I'm going to take each term, a2 over a1, divide it. Negative 5 over 20, that's negative 1/4. And then we'll do a3 over a2. That's 5 fourths divided by negative 5. That's also negative 1/4. a4 divided by a3. That's negative 5 over 16 over 5 fourths. And that also simplifies to negative 1/4. So that tells you that this is geometric. It also tells you r is negative 1/4. And we know what a is because a is the first term of the geometric series. And the first term here is 20. So I can write this in geometric series form as the sum from n equals 1 to infinity of 20 times negative 1/4 to the n minus 1 power. So this is my a, this is my r, and this, of course, then is going to be 20 over 1 minus negative 1/4, which is 20 divided by 5 fourths. 20 divided by 5 is 4, divided by 1/4, so I multiply by 4 again, that's 16. And this is since the absolute value of r is 1/4, which is less than 1 by the geometric series theorem. Now, you do need to get in the habit of specifying whether the series converges, even though it's clear that since we got a value, it converges. You're generally going to be asked to specify, does the series converge or not? So I just want you to get in the habit of actually writing that every time. Okay, so that's it for that example. Let's move on to another one. Determine whether the series is convergent or divergent. If it is convergent, find its sum. So when I look at this sum, what I see is all of my terms involving n are in exponent positions. And if we look at the general formula for a geometric series, we see that any terms involving n are all in an exponent position. So when I see that, I think it might be possible to write this as a geometric series. But if I'm going to do that, I'm going to have to rewrite this a little bit. So how can we rewrite this? Well, 3 to the 2 times n can always be written as 3 squared all to the n power, because when we raise an exponent expression to another exponent, we multiply them. So we can do that in reverse. And 2 to the 2 minus n can always be written as 2 squared over 2 to the n. So this is like applying our basic algebra exponent rules, but backwards. So I'll rewrite this a little further. 3 squared is 9, so this is 9 to the nth power times 4 all over 2 to the nth power. And I can, if I have two expressions with the same exponent and they're dividing or multiplying, if the exponents are the same, I can combine them into one exponent expression. And I'm also going to put the 4 in front just to fit my normal notation. So this is really 4 times 9 over 2 to the nth power. Now this is not quite the standard form for our geometric series, but it's close, because we normally write n minus 1th power. And I also want students to get in the habit of that, because if you don't make that habit, you will often evaluate these things incorrectly because you will misidentify the value for a. So since I need to have the n minus 1 power, what I'm going to do is just take out a factor of this. So that's 9 halves times 9 over 2 to the n minus 1 power. And we'll do one more rewrite here. So 4 over 2 is 2, 2 times 9 is 18. This is 18 times 9 halves to the n minus 1 power. But this series diverges since the absolute value of r is 9 halves, which is greater than 1 by the geometric series theorem. Okay, that's it for that one. Let's move on to another example. Okay, so now we're going to tackle this type of problem, which is taking infinite repeating decimal patterns and trying to write them as a ratio of integers. So the first thing we have to figure out is how to rewrite this as a sum. And 31 here is in the hundredths position. So I can write this as 31 over 100 plus the next 31 is in the 10,000ths place plus the next 31, which is in the 1,000,000ths place, so forth and so on. So this is the sum from n equals 1 to infinity of my first term is a, right? So that's 31 over 100. And r is the thing that I'm multiplying each term by. And it should be easy to see that I'm multiplying each term by 100. If you're not totally sure, you can always double check by explicitly dividing a term from the previous, dividing a term by the previous term. And so what do we get here? This simplifies to 1 over 100. And so this series is geometric and equals 31 over 100 divided by 1 minus 1 over 100, which is 31 over 100 divided by 99 over 100, and that simplifies to 31 over 99, since the absolute value of r is 1 over 100, which is less than 1, by the geometric series theorem. Okay, that's it for that one. Next example. Show that 0.9 repeating is 1. So 0.9 repeating looks like this. But we need to write that as a sum, which is 9/10 plus 9 over 100 plus 9 over 1,000 plus ... which is the sum from n equals 1 to infinity of 9/10 times 1/10 to the n minus 1 power. Since again, I'm multiplying each term by 1 over 10. Now I can apply my geometric series theorem, and I get 9/10 over 1 minus 1/10, which is 9/10 over 9/10, which is 1. And again, this is since the absolute value of r is 1/10, which is less than 1, by the geometric series theorem. So this is a common misunderstanding. Many students get tripped up on the fact that 0.9 repeating is 1, but that's usually because of a misunderstanding of what 0.9 repeating means. And that's what we're trying to express here, to understand that when I talk about 0.9 repeating, I'm actually describing this infinite sum, and the value of an infinite sum. What we're asking is, what's the limit? What number is that sum approaching? And that sum is approaching 1. That's what we mean by 0.9 repeating. Okay, so moving on. Find the sum of the series from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. So this sum looks a lot like our geometric sum, but it's a little bit off because our geometric sum starts from n equals 1 to infinity, not n equals 0. And also, we should have an exponent, n minus 1 power, but I need to change both of those things. So what I'm going to do is I'm going to shift my index up to 1, and I have to change anywhere I had a value for n, I've got to change it in this expression. And how do I change it? Well, since I increased n by 1, I subtract here to compensate. Now, if you're not totally sure if that makes sense, plug in the n values and see what happens. When n is 0, get x to the 0. When n is 1, you get x to the first, x squared, so forth and so on. And now we look over here, n equals 1, I get x to the 0, plus x. When n equals 2, I get x to the first power, plus x squared, plus dot, dot, dot. So we get exactly the same expression, just notated in the standard form for our geometric series. Now I will tack on that I need a little a here, but a is just 1 in this case. So I apply my geometric series formula. And I can do this since we were given that the absolute value of x is less than 1, and by the geometric series theorem. So this is sort of like an early introduction to something we're going to deal with more rigorously later, but this is the fact that I can represent a function as an infinite polynomial. So I have an arbitrary function, 1 over 1 minus x, and I can actually represent it by taking this infinite polynomial instead. And that's going to be a super big deal down the line. But for now, we'll just kind of leave it where it is. All right. Moving on. Okay, so now we're going to look at a very important series called the harmonic series. This series is the sum from n equals 1 to infinity of 1 over n, which is equal to 1 plus 1/2 plus 1/3 plus dot, dot, dot. And so theorem, the harmonic series theorem says simply that the harmonic series is divergent. So that is to say the partial sums of these terms grow unbounded to infinity. Now, one thing I want to point out, 1 over n in this case goes to 0, but the sum of these terms, 1 plus 1/2 plus blah, 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 plus 1 over n, this goes to infinity. So one of the most common mistakes that students make in dealing with series is they think that they can just look at the sequences. If they know if the sequence converges or diverges, that'll tell them if the series converges or diverges. But that is never sufficient, and that's exactly why the harmonic series is such a key example, because here we know that the sequence 1 over n does converge. It approaches 0. But when I add these terms together, I get something that approaches infinity. So let's prove that. Now, it's a little bit of a rough proof. It's not written too formally here, but it should get the idea across. So consider the partial sums of the form s sub 2n. So I'm looking at the second partial sum and the fourth partial sum and the eighth partial sum. I'm just looking at the partial sums where our number of terms is a power of 2. And so the second partial sum is 1 plus 1/2. And the fourth partial sum is 1 plus 1/2 plus 1/3 plus 1/4. Now, I'd like to simplify this expression a bit. So what I realize is that, hey, 1/3 is bigger than 1/4. So I can rewrite this expression as being bigger than 1 plus 1/2 plus 1/4 plus 1/4. And that lets me simplify the whole thing to 1 plus 2 over 2, right? 1 plus 1/2 plus 1/2. Now I'm leaving it as 1 plus 2 over 2 for a reason that you'll see momentarily. But let's first look at the 8th partial sum. So here I get 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And I have that 1/3 is bigger than 1/4. But also that 1/5, 1/6, and 1/7 are each bigger than 1/8. So that tells me that the whole expression that I started with, the 8th partial sum, is bigger than 1 plus 3/2. And in general, what I see is s sub 2 to the nth power is always bigger than 1 plus n over 2. So like, for example, s sub 16, I know is going to be bigger than 1 plus 16 over 2. And s sub 32. Sorry, that's not quite right. S sub 16 is the same thing as saying s sub 2 to the 4th power, which is bigger than 1 plus 4 over 2. And so s sub 32, that's s sub 2 to the 5th power. And we know that's going to be bigger than 1 plus 5 over 2. The whole point being that if all of those partial sums are bigger than 1 plus n over 2, then when we take the limit, since this thing goes to infinity, the partial sums have to go to infinity, and so the series diverges. All right, well, that's it for that example. Now let's go on to an important theorem. So this theorem says if a series converges, then the limit of terms is 0. So again, this is where students get a lot of confusion, because this is basically the opposite of the statement that we just showed doesn't work. So let's go back up here. Here, we had the terms going to 0, but the sums do not. They approach infinity. They diverge. So this is quite the opposite statement. So even though the terms going to 0 does not give us convergence necessarily, if we already know that the series converges, then we do know that the terms must have gone to 0. So how do we know that? Well, let's take a look at a proof. So we look at the partial sums. S sub n is a1 plus a2 plus ... plus a sub n minus 1 plus a sub n. And we're also going to look at the partial sum of the n minus 1 terms. So here I've only added up a1 through a sub n minus 1. So one less term. And that means that when I subtract these two partial sums, I'm going to get a sub n, because all the other terms are going to cancel, and all I get left with is this term. So now when I take the limit for both sides of this equation, I've got the limit of s sub n minus s sub n minus 1 equals the limit of a sub n. I can split this limit on this difference, and I know that the limit of both of these partial sums are both still s. And I know that because even though I'm adding one term less here, I'm still going to keep adding more terms when I take the limit, and I'm going to end up adding all the same terms that I add in s sub n. So that means s minus s is the limit as n goes to infinity of a sub n, and that means the limit as n goes to infinity of a sub n is 0. So again, when a series converges, you know that its terms go to 0, but not the other way around. So this does give us a test for divergence. if the limit of the terms does not exist or is not 0, then the series is divergent. Because again, if the series was convergent, those terms would have went to 0. So if those terms didn't go to 0, it couldn't have been convergent in the first place. So the test for divergence. Again, notice this says the test for divergence. There is no quote-unquote test for convergence, but it's a really, really common mistake. The test for divergence says if the limit of terms does not exist or is not 0, then the series diverges. But be careful, because the limit of the terms being 0 doesn't imply the series converges. It's not enough. It's not a sufficient condition. Okay. Let's go ahead and take a look at example 9. Show that the series from n equals 1 to infinity of 4 times n to the 4th over 5 n to the 4th plus 7 diverges. So what I'm going to do is take a look at the limit of the terms a sub n. So here I'm looking at the limit of 4n to the 4th over 5n to the 4th plus 7. I multiply by 1 over n to the 4th, top and bottom. This gives me the limit as n goes to infinity of 4 over 5 plus 7 over n to the 4th. This term goes to 0, and this equals 4/5, which is not 0. That implies the series from n equals 1 to infinity of 4 n to the 4th over 5 n to the 4th plus 7 diverges by the test for divergence. Okay, that's it for that one. So now we're going to list a few properties about convergent series. And the key here is convergent series. These properties are not necessarily true for divergent series, so don't try to apply them to divergent series. Okay, the first one is that I can factor constants out of a sum, right? So if these infinite sums converge, both converge, I can take, if the infinite sum of a sub n converges, I can take the constant multiples by each term and factor it out and put it in front of the series. I can split up my sum term by term. So if I have a sub n plus b sub n, I can split it into the series of a sub n plus the series of b sub n. And the same thing with the difference of terms. So, example 10, determine the convergence of the series from n equals 1 to infinity of 4 plus 2 to the n over 3 to the n. So, I'm going to split up this sum, n equals 1 to infinity, of 4 over 3 to the n plus 2 to the n over 3 to the n. And now I'm going to split the series into 2 on that sum. Now this only works if the resulting series both converge. So if I found that either of them diverged, I'd have to erase this work and go back and think of something else. But I have a hunch that they're both going to converge. So I also, while I was at it, I rewrote 2 to the n over 3 to the n as 2/3 to the n. And now I'm going to put these in my standard geometric series form. So this is 4 times 1 over 3 to the n, but I can pull a factor of 3 and write this as 1 over 3 to the n minus 1 power, plus the sum from n equals 1 to infinity, and that's 2/3 to the n, which is 2/3 times 2/3 to the n minus 1 power. And so both converge with the absolute value of R1 being 1/3, which is less than 1, and the absolute value of R2 being 2/3, which is also less than 1, by the geometric series theorem. And they're equal to 4/3 over 1 minus 1/3 plus 2/3 over 1 minus 2/3. That's 4/3 over 2/3 plus 2/3 over 1/3. And that's going to be 4 over 2, which is 2, plus 2 over 1, which is 2. And that's 4, barring any silly arithmetic mistakes. Okay. Moving on to our last example here. Show that the series from n equals 1 to infinity of 1 over n times n plus 1 is convergent, and find its sum. So since I don't have any theorems that are going to help me directly with this one, this doesn't look geometric because our expression n is not in the power position for the expression. That tells me that if I want to find its sum, I probably have to figure out a formula for the partial sums. So that's kind of your hint. It's actually, in general, really, really hard to find a sum for a series. There are specific cases where we can, like geometric series and some of the earlier examples. But in general, if we're finding the sum of a series, there's a good chance that we have to find a formula for the partial sums if we don't already have a theorem, like the geometric series theorem, to evaluate it for us. And in this case, this is a special class of series that we call telescoping series. So you'll definitely see more like this, and you'll see why it's called a telescoping series soon. So the first thing I'm going to do is take a look at my expression inside the series, 1 over n times n plus 1, and realize that that looks like those old partial fraction problems we used to deal with. So I'll rewrite this as a over n plus b over n plus 1. And I'm going to find my common denominator and blah, 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 and skip that little bit of the work. So I get a times n plus 1 plus b times n. And I'm going to solve this equation to find a and b. And I'll do that by plugging in first n equals 0, which gives me a equals 1, and n equals -1, which gives me 1 equals negative b, so b equals -1. And I'm going to take those values back up here to my series and rewrite the series in this form. N equals 1 to infinity of 1 over n minus 1 over n plus 1. And this is going to let me write out the partial sums. So when n is 1, I get 1 over 1 minus 1 over 2, plus, when n is 2, I get 1/2 minus 1/3, plus 1/3 minus 1/4, plus dot, dot, dot. And then, since I'm running out of room, I'll just do a second row here. Generally with these problems, however many terms you used at the beginning, you should probably write that many terms out at the end. Again, there's infinitely many terms, so you can't write them all. And then when we go to write these terms at the end, start with your nth term, right? You're starting at the end of your partial sum. I'm adding n terms together. So go to the end and write your 1 over n minus 1 over n plus 1. And just like n was increasing by 1 when we went from left to right, our n values are going to decrease by 1 from right to left. So we go 1 over n minus 1, minus 1 over n, and 1 over n minus 2, minus 1 over n minus 1. And the whole key here with this type of series is to recognize that you can do some cancellation here, that we expanded the partial sum, and then we can cancel -1/2 and 1/2, -1/3 and 1/3. Likewise, this -1/4 is going to cancel with the next term. And this 1 over n minus 2 will have been canceled by the term before it. And this cancels this, and this cancels this. And the only terms in this case that are left uncanceled are 1 and -1 over n plus 1. So we can simplify this expression to 1 minus 1 over n plus 1. And that's why we call it a telescoping sum, because the partial sum expands out and then contracts down like a telescope. And one thing I do want to mention, that for other telescoping sums, they might not cancel as cleanly. You might have to write out a few more terms, and maybe the first 2 or first 3 terms will get left behind with the other terms being canceled. But that you just have to deal with on a case-by-case basis. So you got to write out enough terms that you can see where the cancellation is happening. Okay, so that should have just said s sub n, not s sub n plus 1. So now I'll take the limit, because my series of my terms, 1 over n times n plus 1, from n equals 1 to infinity, is by definition the limit of the partial sums. So that's the limit as n goes to infinity of 1 minus 1 over n plus 1. And that second term goes to 0, so that limit is just 1. So of course that means the series converges, and we also know the value of its sum. All right, that's it for this video. Thank you for watching.